Okay, this is 8.5 Systems of Inequalities. I want you guys to go ahead and start off by taking 2 seconds and graphing 2x plus 3y equals 6 to get our brains warmed up. Okay, so when we graph this, we see that I can actually cover up this 3y right here, knowing that I'm plugging in 0 for y to find out this is my x-intercept. So that gives me that x equals 3 for my x-intercept. This is my y-intercept when I plug in x to be 0. And then this is the line that I have, okay? Okay, linear inequalities in 2 variables and their solutions. So a solution of an inequality in 2 variables, x and y, is a set of ordered pairs of real numbers with the following property. When the x-coordinate is substituted for x and the y-coordinate is substituted for y in the inequality, we obtain a true statement. Each ordered pair solution is said to satisfy the inequality. So just like before, we can have multiple answers that satisfy the inequality. Okay, so graphing a linear inequality in 2 variables. You replace the inequality symbol with an equal sign and graph the corresponding linear equation. Now this is where it becomes super important. We have to recognize that there is a difference between a solid line and a dashed line. So we draw a solid line if it has this extra ink, and a dashed line if it's just the less than or greater than. Just like we used to use open circles and closed circles, we're now using solid lines and dashed lines. Then you're going to choose a test point. Don't pick a point on the line, but pick a point in one of the planes where it cuts. So if we look at this guy down here, we see that here's our line. And if I pick a point right here, or if I pick a point right here, I should be able to test and see which is true. Down here, it's true if it's less than 0 or less than 2, and here's if it's greater than 2. So that allows me to kind of pick and choose where I'm going. Okay, so to do this, to graph this, I first want to graph the line. So what I'm going to do is I'm going to plot my line. I know that my y-intercept is at 3, and then my slope is -2. So that's down 2 over 1, down 2 over 1. And I can keep doing that. Now the important thing to recognize here is my sign. So I know that it's just greater than. So that means it's going to be a dashed line. This is where dashed versus solid is going to be important. So if we draw that in, it looks something like this. So I have a dashed line, I have arrows in both directions, so we know that this is our dashed line, that y is greater than -2x plus 3. So now what I'm going to do is I'm going to pick some points that are not on the line. So let's say I pick a point out here at like 4, 0. I want to see if that one is greater than or less than, and let's say we also want to pick -2, 0. Neither of these are on the line. I just want to find out which side I need to shade. So if I plug it in, I have 0 is greater than -2 times -2 plus 3. Is 0 greater than 4 plus 3? Is 0 greater than 7? No way. That means it has to be shaded on the other side. Now we can check that too. If I plug in a 0, that's going to be greater than -2 times 4 plus 3. So is 0 greater than -8 plus 3 or -5? Yeah, that's true. So that means I'm going to shade this side of the line. So this is the side I want to shade in. And we're going to use the shading to demonstrate what the inequality is. So when we graph inequalities, it not only needs a solid or dashed line, but we also need to have shading on one side of the line. Why don't you take a second and go ahead and graph this inequality. Remember, you need a solid or dashed line as well as shading on the curved side of the graph. So this is the solution that I came up with. I graphed down here at -4, and then I went up 3, right 1 to get my solid line, and I used solid because it was less than or equal to. I picked 2 test points, one from each side, and I saw that this side was less than that. So this is the side I graphed. So this is your equation, or this is your solution. Okay, so without having to pick test points, you can just look at them and realize what side you need to graph. If you have it in y equals mx plus b form, if it's greater than mx plus b, then you're going to graph the half plane above the line. So we might have an equation, so this is y is greater than mx plus b. So I might have a dashed line like this. Then that means I want to go above the line, so I would grade on this side, I would shade on that side. Whereas the line might actually be dashed in this way. And if I want greater than, I have to go above the line, so it would be on this side. So kind of thinking about if I were to go straight up or straight down from a specific point, where would that direction go? The same thing could also be said for saying that I have y is less than mx plus b. And if I have my two graphs with some lines dashed through them, and I want less than, it's going to be down here, and it's going to be down here. So that's a good way to kind of just recognize. Now, vertical lines and horizontal lines are a little bit different. Vertical lines, as long as the x value is on the left-hand side, you can use this as an arrow, and that tells you that I'm going to be greater than, so I need to be this side. I'm pointing in this direction. Whereas if I'm less than, I'm going to be on this side because I'm going to the left. Same with horizontal lines. If y is greater than b, it's going up. Whereas if it's less than b, it would be going down. Your calculator also might have a shade feature that you can use, so you can investigate and see if that's true. Though you'd have to isolate y by itself in order to use that function. And most of the time, the calculators are not going to distinguish the actual line that you drew as solid or dashed, so that's going to be up to you to recognize and to know when to use solid lines versus dashed lines. Okay, take a moment and solve this inequality on your graph. X is less than or equal to -2. All right, this is the solution that I came up with. I had my solid line here at x is equal to -2, and I know that I'm going less than, so I need to be on the left-hand side of that line. Okay, take a moment and solve for y is greater than 1. Graph that for us on your plane. So this is the solution I came up with. Now it's important to recognize that my line is dashed because I only have a greater than. So greater than means I'm on top of, so I'm up here, and I have a dashed line, so at 1. Okay, so it is possible for us to have 2 or more linear inequalities that make up a system of linear inequalities. So we've seen it when we have one linear inequality right here. We know how to solve and how to shade. And if we have 2, you're just going to overlap them and graph them on the same graph. And the important thing to keep in mind is you want to look for the one that has all the shading. So this one here has, a dashed line there. Okay, so I see that I have this dashed line, and I'm above it. I'm above it because I am going to be greater than that dashed line. Whereas over here, I see that I'm still at that same dashed line. I'm still greater than that dashed line. But now I have a new one here. And I have this new line here in red. And I'm greater than it too. So I'm on this side. So basically what we're trying to figure out is where these two lines intersect and where all the shading is. So over here you can see that all the shading takes place in this point right here, in this little weird shape. So that's what's going on right here. So this does not satisfy less than 1. It has to be an open circle there because we know that this is a dashed line that goes through here. So this is your final solution set. So now let's take our knowledge of this and graph the solution set of this system of inequalities. So we have a parabola and a line. So take a minute, graph them, see where their shadings intersect, and then that's going to be our final solution. Okay, so when I graph this, I first graphed my parabola in black, and that's this guy right here. Okay, so if I wanted to label those points, I could. This is at 0, 4, write that a little nicer. So this is 0, 4. This is at 1, 3. This is at negative 1, 3. And so forth. You can also see on the red graph, I've graphed this y is less than or equal to negative 3x plus 2. So what I did is I used two different colors, and then I did my final solution. I shaded the final in blue. So you can see that if I am less than my parabola, I would want to be inside the parabola, and you can do that by picking a test point. So if I picked this point right here inside at 1, 0, and I plug that in here, well, negative 1, so 1 squared is 1 times negative is negative 1, plus 4 is 3, and 0 is less than 3, so I have to shade inside my parabola here, okay? If it had been greater than, then it would have been all on the outside of that parabola. Now, if I have y is less than or equal to this line here, I know that I have to be below that line, so it's all of this stuff out here, but ultimately all I need is my final solution where they both agree, and that's inside this dashed line. There's a hole here for where that vertex is, where those two things intersect, and then I have a solid line taking me down all the way. All right, take a moment, see if you can read this, come up with an inequality, and then graph it. So coming up with an inequality here, the best way to think about it is to figure out what we want x and y to be. So I'm going to say x is my number of kids, and I'm going to say that my y is my number of adults. And so I have some restrictions here. I have a capacity of 3,000 pounds. A kid weighs 50 pounds and an adult weighs 175. So I know that I can have 50x, because however many kids I have times 50, plus 175y for how many adults I have times 175 pounds, has to be less than or equal to 3,000 pounds. If I'm over 3,000 pounds, then I'm going to cause it to break. So we want to figure out what we can graph here. So when I did that, I solved and I found my two intercepts here. I found out that when I have no adults and only kids, I can have a maximum of 60 kids in that car. And yet when I have adults and no kids, I can have 120 divided by 7, or about 17 people, right? So I went ahead and graphed those two things right here. And then I know that I have to be keeping x and y positive. So these are actually more of our restrictions, and we'll talk about that a little bit later. But if I have these two right here also being restrictions, then what I'm able to do is figure out, am I supposed to be out here or am I supposed to be under here? And so if I'm greater than 3,000 pounds, I'm going to be out here. But since I'm less than, I'm going to be right here. Okay, so the intersection of two regions results in the green region at the top of the parabola. So that's this section right up in here. This is the section that we're looking at. And so I want to know which two inequalities would give this intersection. Well, the two lines are exactly the same. So the two equations are exactly the same in all the choices. But if you notice, the inequality signs are different. Now, I know that I'm less than this parabola. So I know right away I can't be choice A and I can't be choice C because I'm less than. I'm underneath that parabola. Now I look at the line and I notice that I'm above the line. So I have to be greater than. So my only choice here is B. I have to be less than the parabola but greater than the line.